Okay, this new unit in this video, it's kind of like a three-part video. We're talking about digraphs and their application. In this video one, we're talking about just what a digraph is. It's just a little separate piece of graph theory. Okay, and then with digraphs, we have a bunch of different applications, but today is just all about the basics. Okay, digraphs are directed graphs. Digraphs for short. So a digraph is a graph in which the edges have a direction associated with them. We call it digraph for short. They're used to represent precedent relationships in scheduling problems. That's the biggest application we look at. Okay, so like a task has to be completed before moving on to another task. The arrows represent the direction in which we're going. Okay, so now instead of the edges being called edges, they're called arcs. That is simply just an edge with a direction associated with it. Now previously it didn't matter how we said an edge. We could say edge AB or BA and it would mean the same thing. But now when we're talking about arcs, order matters. Okay, so like arc XY and arc YX are two separate things. If I say arc XY, I mean from X pointing to Y. If I say arc YX, I mean coming from Y and pointing towards X. Okay, so just keep that in mind. It is important how you write, which letter goes first. Okay, so we still have some of the common same things that we do in regular graphs. We still have paths. Okay, a path is a sequence of arcs such that each is adjacent to the one before it and no arc appears more than once. You list the vertices by the order that you travel. So basically what we're saying is you can only travel in the directions of the arrows, you can never come backwards. So an example, say from vertex A to vertex D, would be maybe A to B, B to D. I'm following the arrows. A, B, D. I could have gone A, C, D. I could have gone, well, that's really about it as far as A to D goes. But I could have gone like A, C, E. Oh no, I could have gone A, C, E, D. I mean, that's another example. Okay? So you're just following the directions of the arrows. Now, instead of having cycles in these groups, we have things called, circuits, we have things called cycles. Okay, they're not called circuits anymore, they're called cycles. But it's pretty much the same definition. It's a path that starts and ends at the same vertex in a diagram. I like to think of bicycle, cycle. You're going in one direction constantly in a circle, in a motion, so that's why I think of arrows with that. So an example might be starting at A, following the arrows to C, following the arrows to E, and back to A. A, C, E. So just going to keep that in mind. Okay. Here's some other definitions that you need to know with directed graphs. I don't usually use this one right here, incident to and from. I don't use that terminology when I speak, but I have seen it shown up on final exam questions and in that terminology, so it's important that you know. Okay, so if I have arc AB looks like this. Okay. If I have arc AB in my digraph, then we say that vertex A is incident to vertex B. Think about pointing to. A is pointing towards B. But then B would be incident from vertex A. Think about it's coming from A. So I'm looking at B. B is coming from A. So I usually use the coming from and the pointing to instead of incident. The next one is adjacent. Okay, it's a little bit different than adjacent arcs in my other, or adjacent edges in the other examples. But an arc is adjacent to another arc if one arc begins where another arc ends. So let's look at an example. I want to find an arc that's adjacent to AC. Okay, adjacent to AC. Now, that only happens wherever AC ends. So the next arc has to begin where AC ends. Okay, so like it would have to be either this arc, or this arc. There are three arcs adjacent to AC. CD, CE, and CA. You don't have to list all of them, but I just asked you to list one. But just know what arcs, adjacent arcs mean. Okay. It's also important to know what out degree and in degree are. Okay, so we still have degree in digraphs, but it's kind of broken up into two categories. Out degree of a vertex is the number of arcs that have A as a start. Okay, it's the arrows that are coming out of the vertex. The end degree of a vertex A is the number of arcs that have A as an end. Okay, so have the arrows pointing at A. So for example, if I'm looking at the out degree and end degree of C, okay, well for out degree, we have 3 arcs coming out of it. And we have 1 arc coming into that. That's the end degree. Okay, so my out degree is 3, my end degree is 1. Let's look at D. D's out degree. Okay, well it has no arrows coming out of it. Everything's pointing to D, so its out degree is 0. But if you look back, its end degree, it has 3 arcs coming into it, so its end degree is 3. Okay. So, know those terminologies. Know out degree, end degree, adjacent, incident to and from. I can ask all sorts of questions about that. Alright, you can also draw a digraph given its vertex set and arc set, just like in the previous examples with regular graphs. But the only thing to keep in mind is that order does matter with these arcs. So let's draw it. I'll draw the vertices first. There's 5 of them. And it was G, H, O, S, T. Now, whenever I'm going through the arc set, just make sure that the direction matters. GH means that I have an arrow pointing towards from G to H. GO means I'm going from G to O. OH, I'm going from O to H. ST, I'm going from S to T. From TG, I'm going T to G, so that's the direction I'm pointing. And TH is T to H. So your graph should look something like that. I might ask you to draw a digraph, give the in degree, out degree, talk about incident to and from, adjacency, so just know how to do that. The next example on this slide is pretty much identical to what you're going to see on the text. I will ask all sorts of these questions. All right, like A and B, or A, give the vertex set and the arc set. That should be given. Okay, the vertex set is just listing all of the vertices. A, B, C, D, and E. There you go. A, B, C, D, and E. So there's the vertex set. The arc set, let me give you my advice for doing the arc set for this problem. I always like to start in alphabetical order and just work my way down, because when I'm looking at A, I'm only worried about the ones that are pointing out of A, because order does matter. So like AD would be my first one. AB would be my next one. AE is the next one. So that's all the ones that start with A. Well, then move on to B. Okay, B has 2 coming out of it. Okay, BC and BE. Okay, so you're done with B. If you move on to C, C has 2 coming out of it. Or, I'm sorry, just 1 coming out of it. CD. The next one, D, only has 1 coming out of it, and that's DB. And then my last letter is E, ED. Okay, and so we have 1, 2, 3, 4, 5, 6, 7, 8 edges, and we're done. Okay, so keep up with that. All right, let's do in degree and out degree for each. Let's do in degree for A through E. A, B, C, D, E, A, B, C, D, E. Okay, so for in degree, it's all the arrows pointing into each one. So with A, there is nothing coming into it. There's no arrows pointing at it, so that's 0. For B, there's 1, 2 arrows pointing at it, so 2. For C, there's only 1 arrow pointing at it, so 1. D only has, well, it has 1, 2, 3 arrows pointing at it. And E has 1 and 2. Okay? the out degree are the arrows coming out of it. So for A, it's all three of them. 1, 2, 3. For B, you have 2 arrows coming out of it. 1, 2. For C, you have 1. And for D, you have 1 coming out of it right here, kind of sneaking out there. And E, you have 1 coming out of it as well. So know how to find out degree, know how to find in degree. All right? All right, what about for D? Finding all the vertices incident to B. Okay, so that means all the vertices that are pointing to D. What are vertices that are pointing to D? Well, what about A and D? How about that? A and D. Those are the 2 vertices that are pointing towards B. What are all the vertices that are incident from B? Meaning they're coming from B, or the ones that are B's pointing to. How about C and E? Okay. Not too bad. All right, what about an arc that is adjacent to AB? Okay, here is AB. Well, in order for it to be adjacent, remember that it has to start where that arc ends. So it has to start with a B. That could be BC or BE. BC, BE. It's up to you. What about an arc adjacent to ED in example G? All right, remember that has to start where ED ends. Here is ED. There is only one arc that starts where that ends, and that is DB. How about a path from A to D? It could be anything. Okay, as long as the arrows are pointing from A to D. How about A to B to C to D? Are there any cycles in this diagram? Well, sure. Okay, there's a cycle here. I can kind of see a little circle right here. How about maybe starting at B, going to E, going to D, and back to B? There's an example. B, E, D, B. If you can have arrows that just keep going around in a loop, then that's the cycle. Okay. So know how to do these questions, know all these terminologies, look back over your notes, and this should be a give me problem. Okay, so digraphs are very important. There's a lot of applications that we do with them. Okay, we do, you can read through these on your own. We do some with tournaments, but the biggest application that we talk about the next 2 lessons after this is scheduling. Okay, it's scheduling. So just kind of keep these in mind. This one's going to be really important. It organizes the precedent relationships in a scheduling problem. So we have a visual reminder of what task must be completed. We call these project diagrams. And again, that'll be in my lesson, the next lesson. So let's do a couple examples of digraphs. Going back to that tournament application. Suppose the vertices in the following digraph represent a basketball team, and then an arc from X to Y means that X defeated Y in a game. So like this arc right here, A to B. That means that A beat B. So this is a way to visually represent how the turnout in these basketball games happen. So, which team won the most games? Which team has more arrows coming out of it? Well, you got A with 2 coming out. You got B with 0. C has 3 arrows coming out. That means that C won 3 times. Same with D. 1, 2, 3. So it looks like that C and D won the most games because they have the most arrows pointing out from them. They have the biggest out degree. What about teams won the fewest games? Well, that would be the teams with the least amount of arrows pointing out from them. How about B? B literally has 0 coming out of it. Every team that B played, he lost to. B sucks. Okay. Did any teams play each other more than once? Well, yeah, look at A. A played B, then he said, well, I want to beat him again, so he played him again. Okay? Those are multiple edges, pointing to the same people twice. A and B did. Also E and D. E played D, and then D got ticked off and said, well, I'm going to play you and beat you. So E and D kind of went back and forth winning. So yeah, that's true. Let's do an example ourselves with the tournament bracket. Okay, let's follow the same rules as above. It says, suppose 4 teams play in the school soccer round-robin tournaments. They're just all playing each other. The results of the competition are as follows. So whenever A and B played each other, B wins. Whenever A and C played each other, A wins. So let's make a digraph that kind of follows along with that. So like if I had A, B, C, and D. A, B, C, and D. Not P, D. Okay, so looking at the first arc, AB here, it says that B is the winner. So B is pointing at A. B beat A. So think of him as he's pointing at him and he's saying, ha 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 ha, I beat you. Okay. What about AC? A is the winner. That means A is pointing at C because A beat C. For AD, D's pointing at A. He beat A. He's laughing and pointing. For BC, B beat C. He's pointing and laughing. For BD, D pointed at B. He's laughing at him. And then lastly for CD, D is pointing at C because D beats C. Okay, so there's my project diagram that represents this situation like the previous example. But now it's asking to find a Hamiltonian path and use it to rank the participants from winner to loser. Well, think about what a Hamiltonian path is. Hamiltonian path goes through all the vertices exactly once. And it wants us to rank them from winner to loser. So let's start the path with the winner. Who is the winner? Who's won the most? What about D? He literally has nobody pointing at him. That means he wins all of them. D is the start here. He has the highest out degree. Well, who next? Who has the highest out degree from there? How about B with 2 right here? B would probably be ranked next. Then to who? A with an out degree of 1, and then all the way down to C with an out degree of 0. C is a loser again. C didn't beat anybody. So my Hamiltonian path that ranks my people are D, B, A, and C. Okay. So again, there's a good idea of how a diagram can work in a tournament representation, showing people winning or losing. It can be more than just precedence relationship. It can show some type of relationship where direction matters. Okay, here's another example I want to do before we get into scheduling, and this example kind of leads into scheduling a little bit, and it's a pretty good one. It's pretty applicable. But this is telling you the course catalog at your college, and it's giving the following information regarding math classes. This whole paragraph here is telling you prerequisites. A prerequisite for Calc 3 is Calc 2. A prerequisite for Calc 2 is Calc 1, and so on. Okay, so we got Calc 3 as a course, Calc 2, Calc 1. Linear algebra can only be taken after both Calc 2 and fundamentals of mathematical proofs. The prerequisite for fundamentals of mathematical proofs is Calc 1. In order to take real analysis 1, a student must complete Calc 3 and linear algebra, and in order to take real analysis 2, you got to do real analysis 1. It's a huge mess. Let's simplify this process down, that is the confusing paragraph down, with a project diagram. Now, I'm not good at being able to go from this paragraph to a diagram. So instead, let's kind of organize the data first, then turn it into a diagram. So what I like to do is I like to write down all my classes and all their prereqs, and then churn that in to a diagram. I think that's a good step. You don't have to do the T-chart, but I think it really helps. And I recommend doing that. Okay? So let's list down all our classes first. We have Calc 1, I'll just say a C1, Calc 2, Calc 3. Our next class was linear algebra, I'll just say LA. Fundamentals of mathematical proofs, FMP. What was after that? Looks like real analysis 1. And then lastly, real analysis 2. Okay. So let's read through this again and put all the prereqs. Okay, for Calc 1, I'm not seeing any prereqs in here. Maybe what you took in high school, but no calc prereqs. So none. All right, Calc 2 though, it says You got to take Calc 1 before you take Calc 2. So C1. In order to take Calc 3, you got to take Calc 2. So C2 for that one. What about for linear algebra? Linear algebra can only be taken after both Calc 2 and fundamentals of mathematical proofs. So Calc 2 and fundamentals of mathematical proof. Well, how do you take fundamentals of mathematical proof? You have to take Calc 1. And in order to take real analysis 1, a student must have completed Calc 3 and linear algebra. Calc 3 and linear algebra. And lastly, in order to take real analysis 2, you got to take the first one, so RA. Okay, so there's my classes, there's my prereqs. I think that's going to be really helpful to kind of start off my diagram. And whenever you start a diagram, whenever I start a diagram, I like to start from the left and work my way right. So I want to start with the class that has no prereq. I got Calc 1. And then from there, I like to branch off. What classes have Calc 1 as a prereq? How about Calc 2 and fundamentals of mathematical proofs? So Calc 1 branches off to Calc 2, and it branches off to fundamentals of mathematical proofs. So we've done those two. Okay, what branches off of Calc 2? How about Calc 3? Okay, Calc 3 has a prereq of Calc 2. If we keep going down the list, you notice that linear algebra has two prereqs, so it's going to have two things pointing at it. Calc 2 and fundamentals of mathematical proof. I have to take those two classes. Those two classes have to point at linear algebra in order to signify my prereq. Okay, lastly, from there, real analysis 1, I have to take Calc 3 and linear algebra. So these two courses have to point at real analysis 1. And then lastly, I have to take real analysis 1 before I can take real analysis 2. And if you notice, there it is. There is my project diagram, or just my regular diagram. Okay? So basically I can look at this and tell if I've taken real analysis 2, I've taken every other course on this list. Okay? This is a great problem. Look over this problem. Know how to write this thing out. Okay, you might see one like this on your test. Okay, so those are some applications, but the biggest one that we do is scheduling. Okay, so in this video I'm going to talk about the scheduling basics, and in the next two lessons we talk about all the application of scheduling. So these are just some definitions and terms that you need to understand before we start our scheduling application. All right, when we're talking about scheduling, we're talking about people doing tasks. Okay, those people are called processors. Okay, they're the workers. Okay, so those workers can be whomever or whatever is working on a task. People, machines, etc. Okay, mostly people is what we're talking about. We'll represent them as P1, P2, and so forth. Processor 1, processor 2, and so forth. And they could be doing anything from completing chores to doing a task at work. Okay? So the task is just the job that we're looking at. Okay, these tasks are going to be represented by our vertices. Okay? So a couple things to know about these vertices or these tasks is that a task is going to be indivisible. Okay, an indivisible unit of work that cannot be broken up into smaller units. Once we start it, we got to finish it. Okay, and nobody can help us. Okay, it's going to be carried out by a single processor. These are just all things that we got to keep in mind when doing scheduling. All right, whenever we're doing our vertices, our tasks, we represent them as capital letters. So as we're going through with our scheduling problems, there's a few things that happen when we reach each task. Okay, sometimes a task can be ineligible, meaning a task that cannot be started yet because of precedence relations, because of prerequisites. Like I can't do Calc 2 until I do Calc 3. It's ineligible. Or Calc 1. A task can be ready. When a task is ready, that means I can work on that task. Okay, all the prereqs have been taken care of. When I'm currently working on a task, it says that I'm in execution. All right, I'm executing a task. And when a task is done, it's just simply completed. Processing time. This is the biggest difference between our past examples and now. Processing time. It is the amount of time that it takes a task to be completed by one processor in an uninterrupted work. Okay, we're going to assume there's going to be some robotic behavior, even though that's not necessarily true, but we're going to assume that the processing time is the exact amount of time it takes to do the task. All right, here's the notation. All right, the first letter is the task itself, but in parentheses, that's telling you the amount of time it takes to do the task. So it takes Y amount of time for one processor to complete task X. That's how you read that. So here's an example. W15. Okay, so this means it takes 15 minutes to complete washing the windows, where W represents washing the windows. Okay, so let's keep that in mind when we get to our scheduling basics. And last thing to keep in mind before we start our scheduling examples in the next lesson is what exactly a precedence relation is, as you've heard me talk about that a bunch, and it seems pretty obvious, but let's just give a formal definition. A situation where one or more tasks must be completed, they take precedence before another task can begin. Okay? So you can also have independent tasks that aren't precedence. So those are tasks with no precedence relationships between them. Here's an example. A precedence relation. X has to be completed before I move on to Y. Here are two examples of vertices that have no relationships. I don't care if I do X or Y first. It would be like making your bed in the morning and eating breakfast. It doesn't matter which one you do first. They'll both get completed. I don't have to make my bed before I eat breakfast. I don't have to eat breakfast before I make my bed. Okay? And then lastly, this kind of goes back to that class example. Like this would be like Calc 1 to Calc 2 to Calc 3. Okay, it doesn't matter. Like I know I have to take Calc 1 before I have to take Calc 3. I don't need this extra line. That's called the transitivity property. So whenever I'm like saying the prereqs for Calc 3, I don't need to reconnect Calc 1 to Calc 3 because it's already a prerequisite for Calc 2. Okay? So keep all this in mind for the next lesson. Hold on to this stuff. Look over these notes, and we'll be good to go for our project diagram.